mini section that we're going to cover here is talking about the determinant of a matrix, and basically for Math 110 purposes, the determinant of a matrix is we're going to treat it like a property of a matrix. So it's going to get us a number back when we do that. If you get into linear algebra or anything like that, if anybody was going to venture off into the world of engineering or electronics and things like that, that you do a lot of linear algebra with that, and you do a lot more stuff with matrices, and there's more things that you can use a determinant for. Our basic goal here is just to calculate the determinant of that. And the determinant of a matrix can only be found for what's called square matrices. So square matrices means it has the same number of rows as it does columns. So it's like a 2 by 2 or a 3 by 3, 16 by 16, but it's got to be the same tall as it is wide. That's the definition of a square, and that's what they call a square matrix. And 2 by 2 matrices, it's super easy to calculate the determinant by hand. Anything bigger than that, it gets much more complicated. And so I'm going to show you 2 by 2s by hand, but anything bigger than that, I do not expect you to do by hand at all out of that. So I'm going to show you 2 by 2s by hand and with the calculator, and then I'm going to show you a 3 by 3 with the calculator. We don't get anything bigger than a 3 by 3 matrix when we're doing determinants in 110. If you were, like I said, if you were going to go into like a linear algebra class or some sort of electronics math type class where you do a lot more with the matrices, and the matrix idea, then you would probably need to know how to do much larger ones by hand, just because they require that in those classes. But for Math 110, they don't. So I'm just going to show you how to do that, and we're going to leave it at that. There are ways to use determinants to solve systems of equations, but I don't think it's better than RREF. It's actually more complicated than RREF. And why complicate something that already works? That's my opinion on it. And as far as what's tested on the final exam, you're not going to see anything that tells you to use determinants to solve a system. Even if it does, nobody checks your, if you do it with RREF or determinants, you get the same answer no matter what. So that's why we don't use determinants to solve systems in Math 110, even though it's a possible way to do it. It's a more complicated way of doing it, and I just don't think it's beneficial to you. So I'm not going to require you to do it. So I'm not going to take the time to show you how it would be done. I'm not requiring you to do that. So a 2 by 2 matrix. Let's start with that, and let's start about finding the determinant of that. So a 2 by 2 matrix is, let's just put letters in there for now, and then we'll get the formula down. To find the determinant, sometimes they will write the word or the letters DET and then put the matrix in there. That's one way to signify find the determinant of that. Or they can sometimes write it this way. They'll just use like what looks like absolute value signs. It's just straight up and down bars. It looks like absolute value, but it's around a matrix. And both of those mean find the determinant. That's the notation that's used for that. Sometimes the instruction will just say find the determinant, and it'll just have a matrix listed there. So a lot of different ways they can ask you to do one little thing. Okay, to do it by hand, it's really, really easy. You multiply the diagonal, A times D and B times C, and then you subtract them. That's it for a 2 by 2. That's all you have to do, which is quick. And the reason that I don't do 2 by 2s in the calculator normally, just because by the time I get the calculator out and get the thing typed in, I could have just done the 2 multiplication problems and been done. So I generally don't do 2 by 2s in the calculator. I'm going to show you how to do it, but I usually I'm faster to do it not by typing the matrix in. But I would use the calculator to do the multiplication and the subtraction for me. But I usually won't type that in there. So let's look at one that has numbers in it and see what we can do. So I'm just going to use the absolute value style notation. I like writing it that way because it's less writing. Okay, so that problem says find the determinant of that. If I want to do it by hand, I'm going to multiply the diagonals. 2 times 7 minus -3 times 5. And always, top left is in the front, top right's in the back, as far as what order they're subtracting in. Okay. And then you just multiply that out and subtract. So that's 14 minus -15. So a double negative becomes a positive, and we get 29. Real easy to do by hand on a 2x2. Just as easy to do with the calculator on a 2x2. So if we go to the calculator, I'm going to go to the same place that I would have went to do that augmented matrix before, because I've got to put the matrix into the problem. So second matrix, we'll go over to edit, and lazy me, I'm going to use matrix A again because that's just, I don't have to move anything to get there. And the size I have is a 2x2. So 2 enter, 2 enter. And then I'm going to put those numbers in. 2, -3, 5, and 7. Okay, so I'm just entering that 2x2 matrix just like I had written down there. Second, quit to go back to the regular calculator screen. And this is where I got to do the math with it. So I'm going to go second, matrix, go over to math, and it's the very first option, DET for determinant. Hit enter, and then it says, okay, well, what do you want to do that to? So I just got to pick which matrix I put in. I put in matrix A. So second, matrix, the first one, hit enter, and there's that 29 that I found by doing my hand. So all of that button pushing to get the 29 that I got by just doing the math. That's why I don't generally do 2x2s in the calculator, just because it's so much faster to just, I just know I look at it and say, okay, that's 2 times 7 minus -3 times 5. And I get the same answer out of that without having to type in the whole matrix thing and back and forth and all that. But if I do a 3x3, it adds a ton more operations to the job. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 operations is what it takes to do a 3x3. That's just a 3x3. If you did a 4x4, it's even more. But it goes from doing 1, 2, 3 operations to do a 2x2 by hand. But if you're going to do a 3x3 by hand, it takes 17 operations. I don't generally ask anybody to do a 3x3 by hand. If I were teaching a math 310 class, which is the linear algebra class, those folks would be doing it by hand because they're going to have to do a lot of stuff by hand. And a lot of times the matrix that they're dealing with has a variable in it. And they've got to, you got to do that stuff by hand because your calculator can't handle the variable. So let's look at a 3x3. And we'll do it with the calculator. So again, we're going to find the determinant. I'm going to use this notation this time. The determinant of 6, 2, 4, 8, 9, 3, 1, 2, 0. So we're just going to find the determinant of that 3x3. There's several methods that you can use for a 3x3. One of them is kind of a trick, and another one is actually doing it what's called by minors. But again, you don't have to do it by hand. I don't expect you to. I would expect you to just put this matrix into your calculator and tell it to do the determinant of that. So calculator, matrix, edit, and I have a 3x3 this time, and 6, 2, 4, 6, 2, enter, 4, enter, 8, enter, 9, enter, 3, enter, 1, enter, 2, enter, 0, enter. So we have a 3 by 3 matrix there. Make sure that you've got all of the numbers in there correctly and the signs correctly. So again, it's just like with the systems of equations. One number in the wrong spot or the sign the wrong way on it, it'll change the problem completely. So second quit, and then I want to go second matrix over to math. Tell it to find the determinant. It's the first option. Second matrix, I'm using matrix A, and there I get a -2 as the value. And that's finding the determinant of a matrix. If it were a 4 by 4, again, I'd use the calculator and I'd put in a 4 by 4. If it were a 16 by 16, it'd be tedious to put in, but it'd be how I would do it. I wouldn't do it any other way with that idea there. So using the matrix of the matrix feature of our calculator, finding the determinant of a square matrix. I will tell you the name of the rule for solving. You can solve by what's called Kramers Rule. That's the name of the rule that uses determinants. We don't have to do that. We can use RREF. This is the same thing as RREF. It gets you the same answer on a system of equations. I'm not even going to show you what Kramers Rule is. Just you've heard the word Kramers Rule. So if you hear that word, you can nod your head and say, yes, I've heard of that. Yes. And I would move on with the conversation. If that comes up, I'd probably say, I'm going to go over here and talk to these other guys. You're probably not in a very fun conversation. All right. So determinants, really easy thing. You're going to get a number back. That's what we're doing with that. Okay. All right. So let's do some stuff with matrices, various properties, and work with matrices. And some of it we're going to do with the calculator. Some of it we're going to do by hand. But it's all going to be very, very pretty straightforward stuff. This is some of the easier stuff that we do. You just got to pay close attention to the details. It's not so much algebra logic involved here. It's more arithmetic. It's just on a matrix, so it looks stuff. All right, so let's look at section 5.7, and it's called properties of matrices. And when they say properties, they're gonna talk about row operations. We're going to talk about adding and subtracting and multiplying matrices. We're going to do all those operations with matrices, and then we're going to do some stuff with equal matrices, or what we would call matrix equations, and then we'll get into the last section about matrices, which is inverse matrices. But that's again a very easy idea with the calculator. So let's start with row operations, and I think this may be one of the few things that I really discourage using the calculator for, just because getting the calculator to understand what row operation you want it to do is not easy because of the way that you've got to input that into the calculator. It's just not doesn't make sense a lot of ways. So I think this is one of those things where it's just easier to do it by hand because you're not solving anything. You're just really just working with a matrix. So let's just pick up a matrix. We're going to call this matrix 3, 2, 6, -5. So it's got 4 columns is what we've got there. 1, 7, -9, 4, -8, 10, 2, and -13. Okay, so there's our matrix that we're going to do a row operation to. And what they'll do is they'll tell you what row operation to do. There's no guesswork involved. There's no, nothing that you've got to decode the secret message. They're telling you exactly what to do, and all you've got to do is follow the instructions. So one of the row operations that they might tell you to do would be do something like this: 3 times row 2 change row 2. Maybe that's what they tell us to do. So again, that's just 3 and then a R2. That's a subscript 2, not an exponent. So it's just saying, hey, that R stands for row. The number down here is what row is it? Row 1, 2, or 3. Okay. And then when they put the arrow there, or sometimes they'll put an arrow like that, or sometimes they'll just put an equal sign. It's the same thing. I use the arrow just because that's the way I've seen it my whole life, and it doesn't necessarily always have to be that arrow. It could be an equal sign. All that says is say take 3 times the current row 2, and then make that the new row 2. That's all that says. It says take 3 times row 2, change row 2. Okay, so that means when I work this out, my row 1 is staying the same, and my row 3 is staying the same. Because this right here said row 2 is the only guy that's changing anybody but row 2. And we're going to change row 2 by doing this operation. We're going to say 3 times whatever's there. So 3 times 1 is 3. 3 times 7, 21. 3 times -9, -27. 3 times 4, 12. That booger right there, that's your answer. Which is it seems too easy. It really is that simple as what you're doing here. Okay? So you're taking that and you're doing what they say. Follow their instructions. They're going to tell you what to do. All your job is to just do it, as Nike says. Okay. All right. So I'm going to take, for example, B. I'm going to take that matrix we got there. So if you want to recopy it, you can, or if you just want to start right there at that one, you don't have to take the time to recopy it. So that's our original now. I'm going to take that matrix, and I want to do row 1 plus row 2, but this time I want to change row 1. I'm going to add row 1 and row 2 together and put the answers in the place of row 1. Okay? So that tells me that when I go to do this problem, my matrix that I get at the end, row 2 and row 3 are not changing. They're going to be the same. So I'm just going to go ahead and copy those so that I don't get, kind of math happy here and do too much. Those two are not changing because the only one that's changing is what it says at the end. There it says row 1 is now going to look like what row 1 and row 2 added together was. So I'm going to add, and I'm going to add corresponding spots. So 3 plus 3, they're both in the first spot, so they add together. 3 plus 3 is going to be 6. That goes up there. Corresponding parts here, 2 plus 21, 23. Goes there. -27 plus 6. -21 goes right there. +12 plus 5 plus -5. It'll be +7. That's my answer. Okay. Again, it's just taking what they give us and following directions. Nothing more, nothing less. Okay. All right. Example C. That's the answer we got on example B. Okay, so if you don't want to recopy it, just know that's the answer we got on example B. The row operation that we want to work on this is take 1/3 of row 2 and add it to row 3. And change row 3. 1/3 of row 2 plus row 3, change row 3. Okay. So what that tells me is that I can copy row 1 and row 2. Because row 3 is the only guy that's changing. Or gal, whichever way you want to look at that. Okay. So we're going to follow order of operations on this row operation here. We got 1/3 times something plus something else. So the multiplication happens first. So 1/3 of 3. 1/3 of 3 is 1 plus -8. Would be -7. Okay. Then we take 1/3 times 21. That'd be 7 plus 10, 17. Then we take 1/3 of -27. That's -9. -9 plus 2, -7. Then we take 1/3 of 12, which is 4. 4 plus -13, -9. And we finish that row operation. There's nothing more complicated about row operations. It really is straightforward. Follow the instructions, only changing one row at a time. Okay. One of the instructions that could come up is one that might have row 1 and then it has a double arrow. That just means take row 1 and row 2 and swap them. That's all that means. So that's kind of a special. This just means swap. Swap the row 1 and row 2. That's all that means. The double arrow means swap. That one doesn't come up very often, especially in Math 110, because we're not doing a whole lot with row operations. If you were in that linear algebra class, you would be doing a lot more with row operations by hand. We're not doing much with them, so we're just taking and following some instructions about row operations with matrices, because we're kind of a broad stroke of math stuff in 110. All right, now let's look at a matrix operation of adding and subtracting matrix operations. Is where we're headed next. So let's do adding and subtracting. Adding and subtracting matrices has the same. They both have the same rule as far as the rules for the operations. Adding and subtracting matrices. When you do that, they must be the same size. Okay. That means same rows and same number of columns. So if I'm going to add two matrices together, if one of them is a 2 by 2, then the one I'm adding to it has to be a 2 by 2 as well. If they're not the same, it's not a defined operation. You can't do it. Okay. So they've got to be the same size. You could have a 3 by 5 minus a 3 by 5. That works. You can do that. As long as the sizes are exactly the same, you can add and subtract them. If the sizes are different, it's an undefined operation. You can't do. It means there's no solution. It doesn't work. Okay. So they have to be the same size in order to add and subtract. That's a very important thing because it's not the same rule when you multiply. Okay. So adding, subtracting, they got to be the same size. All right, so let's look at an example of adding and subtracting. When we get into the operations, you can do it with the calculator, and I'll show you how to do that. But adding and subtracting, I generally don't do with that calculator just because I'm just faster at just doing the adding and subtracting because it's not overly complicated. But we will look at how the calculator does it as well because sometimes you might have several matrices that you're trying to do some operations with, you might want to use that to help you keep from, looking at the wrong one, something like that. So let's look at example D. Let's take this one, 5, -6, 8, 9, plus -4, +6, 8, -3. Okay. So here we have a 2 by 2 and a 2 by 2. They are exactly the same size, so that means that you can add them. The way that you add matrices is corresponding positions. 5 plus -4. They're both in the top left, so you put them together. 5 plus -4 would be 1. And then I go to the next spot. -6 plus +6, 0. Then I go to the next spot. 8 plus 8, 16. Then I go to the next spot. 9 plus -3, +6. Corresponding positions. They've got to be the same size so that you have matching spots to put together. If they're not the same size, you can't work any of it. It's got to be exactly the same size no matter what to add or subtract. If I wanted to do that in my calculator, I'll go ahead and show you that. Second matrix, go over to edit, and I'm going to have to use two different matrices here. So I'm going to enter matrix A. I've just got to remember that I'm entering the first one into it. Negatives, or 2 by 2 is what size we're dealing with here. 2 by 2, we got 5, -6, 8, 9. And then I'm going to go to the matrix and edit. And I'm going to go into matrix B this time. So I press the down arrow, select matrix B. It's a 2 by 2. And I'm putting in the second matrix in it. So -4, +6, 8. 8 and -3. So I've put those two matrices into A and B, and now I just need to tell my calculator to add them up. So I would go second matrix, select matrix A, hit the plus sign, second matrix, select matrix B, hit enter. There's the same answer I got without having to type them into the calculator. I generally do not do adding and subtracting alone of matrices in the calculator just because I'm faster at just doing the math. Because you're just matching up spots out of that. So the calculator will do it. I don't think it's beneficial. It doesn't save you much time. Might save you some worry about whether you did the math right or not, or the subtraction correct. But I can just type in each individual problem faster than I can type the matrices in and go back and forth and pick them up. So let's look at another problem. Let's say we had 8, -10, 6, 5, -7, 18, minus 6, -4, 1, 8, 5, 9. So here we have a subtraction problem. Want to make sure they're the same size before you even attempt to do that. So this one is 3 rows by 2 columns. The second matrix has 3 rows and 2 columns. So works. They're exactly the same size. That means I can subtract them. If they're not the same size, you don't have to work it. It's no solution. That does not exist. Not a defined operation, whatever you want to call it. It doesn't work. Okay. So again, it's corresponding spots or positions. So top left and top left go together. 8 minus 6 is 2. And if you want to go side to side or straight up and down, it doesn't matter. I'm going to go row at a time. So -10 minus -4 would be -10 plus 4, which is -6. And then I'm going to do the next row. 6 minus 1, 5 minus 8, -7 minus 5, 18 minus 9. And there I have my 3x2 matrix that I got from that subtraction problem. So whatever size they start out with, if they're already both the same size, then it works. You're going to get the same size back. Okay. All right. Adding and subtracting. Really, really simple idea. The next operation is called scalar multiplication, and it is easy too. So scalar multiplication. I want you to think like distributive property, because that's the way it works. Okay. Scalar multiplication means you're taking an entire matrix and multiplying it by a single number. Okay. For example, 6, -8, 10, 2/3, 4, -13. It doesn't even matter what size the matrix is. If you're going to do scalar multiplication, what they're going to do is they're just going to plop a number out on the outside, like a 3. And they're going to say scalar multiplication, or multiply 3 times everything on the inside. That's all it means. You distribute that 3 that's in the front. This guy multiplies to every single piece that's inside. That's all scalar multiplication really is. So 3 times 6, 18. 3 times -8, -24. 3 times 10, 30. 3 times 2/3, that'd be 2. 3 times 4 is 12. 3 times -13 is -39. And you get a 2x3 matrix back, same size as the one I started with. So scalar multiplication, it's just multiplying an entire matrix by a number that's in front. Scalar multiplication, if you had to do a problem that had scalar multiplication and matrix addition into it, the scalar multiplication, just like order of operations, multiplication happens before addition or subtraction. So order of operations hasn't changed, even though we're in the world of the matrix now. The order of operations is still, please excuse my dear Aunt Sally, it's still the same rules. None of that's changed. Okay? The only thing that really changes is we don't have division with matrices, which everybody said hallelujah on that, because division is the one that always kind of messes us up, especially with that. All right, now, those are the easy ones. The really easy thing is scalar multiplication, and then adding and subtracting is super easy as well. The next thing is multiplying matrices, and it's not quite as easy by hand. So I'm going to show you the rules for that. The rules are not as easy as addition is. Addition, they had to be the same size. Subtraction, they had to be the same size. In multiplication of matrices, being the same size doesn't mean it'll work. Okay, just because they're the same size doesn't mean that you can multiply them together. So multiplying matrices. One thing that you need to know, it is not commutative, which means you can't do it in a different order. With regular numbers, if you said 3 times 2 is 6, commutative property says 2 times 3 is 6. You can change the order and it's the same answer. With matrices, you can't change the order. If it's written this matrix on the left, that matrix on the right, you can't swap the order and get the same answer. A lot of times you can't swap it and even get it to work. Okay, so you can't swap the order when you're talking about multiplying matrices. It's not commutative. That's important to know. The rule for multiplying matrices, the left matrix columns must be the same as the right matrix rows. What that means is if you had a 2 by 3 matrix times a 3 by 4 matrix. Remember, dimensions is always row by column. It's always row in the front, column in the back. So 2 rows, 3 columns, 3 rows, 4 columns. Those numbers have to match that are in the middle there when you look at the dimensions. 3 and 3. What that means is that this will multiply together and give you a 2 by 4 as an answer. The outside pieces tell you what size your answer is going to be. The good news is you get to use your calculator, and it'll throw an error to you and tell you why it won't work when you do this, and I'll show you with that. I'm not going to be stickler on this and say you have to be able to multiply matrices by hand. It doesn't matter to me if you can multiply matrices by hand. You can do it with a calculator and get the right answer. I'm good with it, especially considering you guys, on a short time frame with Math 110 anyway, and the fact that most of us aren't going into an engineering type field where we would need to be able to do this by hand anyway. So what we're going to look at is just taking 2 matrices and multiply them together. Okay, so example G. We're going to say matrix A. I'm going to name these matrices. So matrix A is 1, -3, 7, 2. Matrix B, 1, 0, -1, 2. 3, 1, 4, -1. So not getting very big numbers in there, but it doesn't really matter out of that. So what we want to do is find A times B, if possible. Okay, so what we need to look at is dimensions. So what size is matrix A? It's 2 by 2. Matrix B, how many rows does it have? 2 and 1, 2, 3, 4 columns. So it's a 2 by 4. So we have a 2 by 2 times a 2 by 4. The numbers in the middle match. So that means I will get an answer when I do this. Okay? That answer will be a size 2 by 4 because the outside. So I know I'm going to write something big enough to put a 2 by 4 in there. Okay? What I want to do is multiply that together. Now, if you wanted to do this by hand, shoot me an email, and I'll link you to a video that shows you step by step how to multiply 2 matrices together by hand. I don't feel like it's advantageous for you to sit through that. It's more confusing than it is anything with that, because there's a lot of steps to do it by hand, because it's row times column, and then you got to add row times column, then you got to add. It's a lot of steps to doing it by hand. So I'm all for just doing this with the calculator. So we're going to do it with the calculator, and so I'm going to take these 2 matrices and put them into my calculator. So I'm going to go to clear out everything I've done there, and then go to matrix and go over to edit, and in matrix A, it's a 2 by 2, and I named them A and B for a reason. Okay, and then I'm gonna put the numbers in: 1, -3, 7, and 2. So I put in matrix A from my example. Second, quit. Go back to the matrix, go to edit. I'm going to matrix B, and its size is 2 by 4. I'm going to put the one from my example. So 1, 0, -1, +2. In the second row, I've got a 3, 1, 4, and -1. 2 by 4. It's the right size. Now I'm just going to tell my calculator to multiply those two together. So to do that, I've just got to go to the names part of the matrix menu. So second matrix, matrix A. The way the problem was asked was A times B. So when I put it in my calculator, I've got to put A times B. So A is on the left. So A times second matrix, and then B. Left A, B on the right. Hit enter. It cranks me back an answer that is a 2 by 4 in size. Exactly what I expected. And I got those numbers. That's all I've got to write down. -8, -3, -13, 5. And then some more stuff. On paper. -8, -3, -13, 5. And then the next row was 13, 2, 1, 12. 13, 2, 1, 12. There is the product of those two matrices. Okay. Example H, what if they said find B times A? Same two matrices that I already got entered. They told me to find B times A. Well, I remember what Mr. Isbell said. He said that it's supposed to be, you can't do commutative with that. So I may not even be able to do this. Well, I rearranged it with the dimensions, and I see I've got a 2 by 4 times a 2 by 2, and these numbers in the middle do not match. Because they don't match, that means that this is undefined. Rewrite that in my handwriting. Undefined. It won't work. Well, what if you didn't remember that rule? What if you just went ahead and put the matrices in your calculator and you tried to do it? The good news is your calculator tells you it can't be done. So you go to your calculator and you go second matrix, and we got matrix B in there times matrix A. So I've just put it in there just like I did for example G, but the multiplication is backwards. And it says the error that it gives back is called a dimension mismatch error. What that means is that check this. It says in the notes there, it says check the size of the matrix. It's of lists and matrices. This can work with list as well, but it's the same error. It tells you, hey, you can't do that. It don't work. It doesn't work if you're proper English people. Okay, it doesn't work that way. You cannot do that because the dimensions don't match in the right way. So you get that error to you, whether you remember what the rule is or not. The calculator can kind of steer you in the right direction, and that tells you, hey, I can't do that. I know what I need to write is undefined now because I cannot do that multiplication out of that. All right. Okay, so multiplying matrices, again, calculator is the way to go on that. So make sure that you go back and you learn the process of writing, doing that with the calculator. I'm not going to make you sit through me doing that by hand because it's long and boring and not really helping you any. Doing the calculator is the way to do it. Now, let's look at the next thing in this section, or the last thing in this particular section, and then we'll get to that very last section about matrices for that. So this last thing is called equal matrices. Equal matrices. Sometimes you might hear this called matrix equality. That means the same thing. It's just semantics about how you say it. But here's the deal. You got two matrices or maybe more that are equal to one another. So if a matrix is equal to another matrix, then that means spot for spot they're equal to each other. So let's take a simple one to start off with. 2, 1, P, Q, and then on the other side, we got X, Y, -1, 0. Equal matrix means, hey, whatever's here is equal to what's there. So that means 2 is equal to X. And then 1 is equal to Y. P is equal to -1. Q is equal to 0. Most simplistic way I could do that example there. We're going to do one that's a little more fun next. But the idea is spot for spot. They've all got to be the same size for it to be equal matrices. They're telling you they are. So you've just got to match up spot for spot out of that. So let's do one that's a little bit more fun. Let's say we had this matrix, 7x3, -5, 10y, plus, so we're going to throw in a little matrix addition here, plus 8, -6, 10, 5, 16, 7 is equal to. So here we finally have an equals. So it should be a two row by 3 column matrix that it's equal to. 15, 8 plus 7 is 15. So that's what has to be there. And then 10 and 13. And then the bottom row is going to be 0, 26, and 14. All right. What we've got to do here is find X and Y. All right. So we're going to set up an equation for X, and we're going to set up an equation for Y and solve each of them individually. This is not a system of equations. This is just a matrix equation, or matrix equality is all this is. This is not a system of equations. So it's just we set up one equation for X and we set up a separate equation for Y, and we're going to solve those. Okay. So X is right here in the middle. What part of this second matrix goes with X? The -6, and on the third matrix, it's the 10. We look at our equation, we've got nothing in front, so that's just going to be plain X plus -6 is equal to 10. X plus -6 equals 10. And we get the equation for X. And we just solve that just like we would any equation way back. Okay, so we're going to add 6. X is equal to 16. What would the equation be for Y? Y plus 7 is equal to 14. We're just taking the matching spots and going across the matrix, the equal matrices. Okay, so we just subtract 7, and there's Y is equal to 7. Not bad. It really doesn't get much more complicated than that. About the only complication that there might be would maybe be a scalar multiplier that's out in the front that you would need to multiply first before you do your addition and subtraction. So, but matrix equalities, really just simple equations that you should be setting up to solve for those. A really simple idea. All right. One more little matrix section here, and then we will take a break and then come back and finish off the course after this. So let's get section 5.8. And this is a calculator skill that we're going to talk about, and it's really easy to do. Maybe not as easy to understand, but it's easy to do. So matrix inverses. All right. Matrix inverses are multiplicative inverses is what it ends up being. So, or think of it in terms of, when we're talking about regular numbers, 3 and 1/3, what's the relationship with those two? 3 and 1/3. 1/3 is the what of 3? What's the word when you flip something over? Reciprocal, right? 3 and 1/3 are reciprocals of one another. A inverse matrix is like a reciprocal matrix. It's just not flipped over. It's why you don't think of it as flipped over. It's a multiplicative inverse, but it's a reciprocal. It's the same property in regular numbers. When you multiply 3 times its reciprocal, you get 1 back. And what that is called an identity. 1 is the identity, multiplicative identity when you talk about numbers. What that means is no matter what I multiply times 1, I get the same thing back. So when we talk about matrices, they have an identity. When you multiply a matrix times its inverse, and remember our function notation for inverse was the -1 exponent thing. Remember us doing the function inverses? What we end up with is an identity matrix. Okay, so there are different identity matrices depending on size. When we talk about inverse matrices only happen for square matrices, just like the determinants was. It has to be a 2x2, 3x3, 4x4. That idea out of the identity matrix for a 2x2. Another name for that is I sub 2. It's a 2x2 matrix that has ones and zeros in it, just like that. Have to be in those spots. That's I2. If I say I2, that's what I'm talking about, is that matrix. If I say I3, it's a 3x3 matrix with a diagonal of ones going down that center diagonal. That's I3. I4, four by four with that diagonal of ones down the center. I5 and I6, you could keep going forever on what they look like. Okay. Reason we need to know what that looks like is because we can test if two matrices are inverses of one another by just multiplying them together. If we get one of these I matrices, then we know they're inverses of one another. Okay. So, and I want to show you how to get your calculator to find an inverse. And then I also want to show you how to verify their inverses of one another. Okay. So let's find the inverse matrix, if possible. And I say if possible because some matrices are what's called non-invertible matrices, and just means that their determinant is 0, and the reciprocal of 0 is undefined. You can't do that. You can't divide by 0. So that's the idea of it. But let's look at an example. Let's say it's matrix A, and here's the original matrix: 1, 0, 1, 2, -2, -1, 3, 0, 0. So that's the matrix. And we want to find the inverse. So A inverse. That's what we're looking for. So the notation is just a little -1 exponent. Okay. So what we need to do is put that matrix into our calculator. 3x3 matrix into our calculator, and we're going to have our calculator find the matrix, the inverse matrix for us. So second matrix, I'm going to go over to edit, and I have a 3 by 3. And I'm putting in the 1 from example A. So 1, 0, 1, 2, negative 2, negative 1, 3, 0, 0. Okay. Give you a chance to get that put in. So go into matrix, over to edit, and I'm just using matrix A again. It's a 3 by 3. And then I'm putting in the numbers from that matrix that we're using for example A. Once you've got that into your calculator, you go back to the regular calculator screen like you were going to add or subtract or maybe even multiply it or something. And we're just going to tell the calculator to find the inverse of that matrix. So what we've got to do is get the matrix we want to invert. So second matrix, I put it in matrix A, so I'm going to grab A by hitting enter. And then your calculator has that X inverse button over here on the left, just underneath math. We're not going to hit second. We're just going to hit X inverse and get the little -1 exponent. That's A inverse. All I got to do now is hit enter, and it's going to find me the inverse matrix for matrix A. It's got a lot of decimals in it. How do I change decimals to fractions? Math, enter, enter. There is the inverted matrix. That is the inverse of matrix A. 0, 0, 1/3. -1/2, -1/2, +1/2, 1, 0, -1/3. A lot of fractions in that. Sometimes there are fractions in it. Sometimes there are not. A lot of times there are, though. But notice how it really doesn't have any matching pieces here with the original matrix. You might could find a little bit of a correlation there, but it's really not. What happens in order to find that inverse? Your calculator does a fairly complex series of row operations with that and combines it with a determinant of that original matrix to do that. It's a lot of math going on in the background there. But to find the inverse, you just use A inverse. Now, here's what we can do with that. We can verify two matrices or inverses by multiplying them together. So I'm going to edit matrix B and put in that inverse that I just found. So 0, 0, 1/3, -1/2, -1/2, +1/2, 1, 0, -1/3. So that's matrix B. If I were going to verify that two matrices were inverses of one another, I would multiply them together. Okay, if I multiply matrix A, matrix A, hit enter twice there accidentally, times matrix B. Look what I get back. I get the I3 matrix because I know they're inverses of one another. If I don't get the I3 matrix there on a 3 by 3 for inverses, they're not inverses of one another. If I get anything else in there besides that diagonal of ones and those zeros around it, they're not inverses of one another. So if you had two matrices and they ask you to verify that they're inverses of one another, you can just multiply them together and that gets you the inverses. Or you could just find the inverse of one of them and see if it matches the other. Either way, it does the same verification of that. I like the multiplying one just because I get to use the identity matrix out of that. And this is one of my favorite topics in math is linear algebra with the matrices stuff. But it may not be your favorite. It's mine. It's one of mine. So, but it's a neat idea. Okay, so calculator in there to get the inverse. Use the inverse button just underneath math. get that -1 exponent, and it'll find the inverse for you. Okay. All right. Now, how is that useful? Well, we can actually solve systems of equations using this. I don't generally do this, but it always comes up on the final exam. So I want to go over one where you're using the inverse matrix to solve. And the way that they usually bring it in on the final is they don't make you solve it. They'll say, which one of these would solve this equation? And so it's like a tricky thing where it doesn't give you the answer, but it gives you a setup to find the answers. And that's, to me, some of the most difficult problems to do. So I want to show you that with an example of solving using an inverse. So using an inverse matrix to solve a system. All right, so let's take a fairly simple system, 2x minus 3y equals 4, and x plus 5y equals 2. All right? Now, you have what's called a coefficient matrix. We've talked about an augmented matrix. The augmented matrix has everything in it. A coefficient matrix, guess what it has in it? The coefficients, the numbers that are in front of the letters. So the coefficient matrix is 2, -3, 1, 5. What I'm showing you here is how they can set up a matrix equation in a system. All right. So what they've got going on here is they've got a matrix times a matrix is equal to another matrix. Okay. So remember, just basic algebra idea here. If you had 2/3 x is equal to 10, how would you solve that problem over here on the right? Another way of dividing by 2/3 would be multiplying by the what of 2/3? Dividing by 2/3 is the same as multiplying by its, starts with an R, reciprocal. And remember what we tied together with inverse matrix and reciprocal, that they're the same thing. Okay? So same idea here. If we can multiply by the inverse on both sides, it would solve this problem. Okay? The difference is we have to do it in the right order. Because if this is matrix A, then if we multiply by A inverse times A over here, that's the inverse on the left. Remember, multiplication with matrices is not commutative. So you've got to multiply by the inverse matrix on the left on the other side. Okay? Over here on the left-hand side, just like on this problem over here, those two canceled each other out, and you just got x. Over on the matrix equation, these cancel out, and you just get xy. xy. What we need to do is find the inverse of matrix A and multiply it times the matrix 4, 2. So we've got to enter a couple of matrices into our calculator. Again, this is not the best way to solve a system, but the setup is what they ask you about on the final exam. The setup, the part you need to remember is you got to use the inverse on the left. That's what you need to remember. Inverse on the left. So what's the inverse of matrix A? I don't know. I got to find it. So second matrix, go over to matrix, edit, 2 by 2 this time. And matrix A has a 2, a -3, a 1, and a 5. And then I'm going to go to matrix B and put in that 4, 2. It's got 2 rows, but only 1 column. So that's 4, 2. 4, enter, 2, enter. Now, I need to find matrix A, the inverse of matrix A. So I already kind of know how to do that. So matrix A, and then the inverse button. A lot of decimalage there, just a ton of it. Okay, I could hit math, enter, and it looks a little bit better. Divided by 13. 13 is not a great divisor. It doesn't go into a whole lot of stuff. Now, what I'm going to do with that is I'm going to multiply that answer times matrix B. So I just hit the multiplication symbol and then matrix B. And it gives me X and Y. It's 2, 0. It's really a neat way of solving there. 2, 0. So X equals 2, Y equals 0. Ordered pair is 2, 0. Out of that, using the inverse matrix to solve that. Again, I would prefer that if you were just asked to solve a system of equations, that you would use RREF to solve. That's going to get you the same 2, 0 as the answer. But the way that the final exam asks the question is, how do you set it up to solve it? This is the key. Inverse on the left, solutions on the right. That's what you need to know. Inverse on the left and multiply. That's what you need to know for that one question that seems to always come up on the final is that if the inverse is on the left and you multiply times the solutions on the right, and that's how the setup goes out of that. So it's not necessarily the best way to solve one, but it definitely can help. All right. Suggested problems from these sections, and then we'll take a short break and then come back and finish up the nonlinear systems and stuff like that. Suggested problems will be from 5-1, 7 through 67. Good set. 5-2, 5 through 37, and then there's a set little 53 through 61. 5-3, that was the determinants. I don't figure you need a ton of practice with that, but offer it up just anyway. So you got some things you can do. 5-7, that was the operations there, and then 5-8 was the inverse stuff with that. So that's the matrix things that we're going to do there, and a lot of calculator stuff involved there. So let's take about a 10-minute break here, and then we'll come back and finish up the last two sections. We'll kind of go backwards in the chapter there and talk about nonlinear systems and then linear programming for just a moment, and we'll be finishing up for the night. So